A very good afternoon to all of you. I'm Ankita Chauhan from NASSCOM Product Council. Today's webinar will be very interesting as it will cover how AI deep technology is being utilized in the healthcare sector. I have Dr. Sunil Kumar Vuppala, Principal Scientist in Philips Research India, who will share his knowledge and experience on the topic Enable Deep Learning with Applications in Healthcare. You can write your questions anytime during the session and Sunil will try to answer most of them after completing his presentation. Plus, do not forget to leave your feedback to help us improve the future webinars. Over to you, Sunil.
Yeah, thank you, Ankita, for setting the context. So we have 1 hour with us to talk on the topic, especially on the enabling the deep learning with applications in the healthcare. So I'm Sunil from Philips Research. So working as a principal scientist and part of the leadership team. So this is the legal disclaimer from NASSCOM. So this is what the agenda we have for today. Because of the wide audience from different organizations, I want to just touch upon the basics of deep learning. So just to recap in terms of what are the different types of learning we have. And then from there, we will go to why DL is important for the healthcare. What are the trend changes? Then I will give my top 10 list of applications of deep learning in the healthcare that is generic in nature. Then I try to give a multi-dimensional view because most of the attendees are coming from the technology background. So how you can view this kind of 10 applications in multi-dimensions. That's what my plan for the first 30 minutes. Then next 20 minutes, what I was planning is to cover these topics, some of the applications, because we don't have enough time to cover all the topics, maybe at least some 4 or 5 topics, especially the personalized medicine or medical imaging and what kind of explainable deep learning, what we mean. Then how do you improve the performance of the DL model built? And the latest edition will be on the synthetic image generation. So some topics at least we can go a little more detail so that you will get a view both in the depth wise and the width wise. And at the end, I'm talking about challenges in the deep learning to use the deep learning in the healthcare with some summary and references. That's planned for us. I'll try to keep it within 50 minutes so that we'll have enough time for the Q&A as well. And I'll leave my coordinates for reaching out even if you have some questions for the offline as well. So the first one, what I'm starting, because most of us are in the industry, so I'm sure you will be able to read the Gartner hype cycle. So what I'm showing it to you here is hype cycle for emerging technologies, and it is very latest, 2018. I'm pointing here the where the deep neural network is, the deep learning is. As you see, it's in second quadrant of the Gartner hype cycle, which gives us a view of within next 2 to 5 years. It will be. I hope this will be in a at a product level. Now also a lot of research is definitely going on with a lot of hype, but we will have more clarity on how we can productize and how we can democratize. That's what I mean in the next 2 to 5 years. The expectation is definitely healthcare is also a emerging field to use this AI, and what our focus is more for this session is on the deep learning. So I want to demystify the terms because in the media or in the people who are entering the field, we are using this interchangeably, AI, ML, and DL. So to make my point clear, what we are talking for this session is a deep learning, which is a subset of machine learning. But general AI is beyond machine learning and deep learning, which may include some kind of a knowledge management, logic. So we are not covering the entire AI applications. I try to give the top 10 applications, especially for the deep learning, in a way that will be applicable for the machine learning as well. But if you see what is the fundamental difference of the machine learning and deep learning, why more people are talking about deep learning now? So that's what I'm trying to emphasize my point in this slide. If you see here, what are the problems we are trying to solve now? If I ask you a question as well, is it completely new? Most of you, I am sure you will agree, it's not completely new. But deep learning is taking the moment, even though it has a history of 60 years, it is gaining momentum now, mainly because of these two reasons. If you see the availability of the lot of data, especially the digital data, and we have the compute power to run those. So with that background, we are getting more applications being solved in the deep learning. That is one point. And second point is in the machine learning, we need to do some kind of a feature engineering. So you should be an expert, domain expert to do the feature engineering. That's what I'm trying to show or emphasize in this particular picture. Whereas in the deep learning, if you throw the enough data, maybe at the cost of maybe machine learning may not require those many data points, but this deep learning, I'm expecting more features. But the benefit is you can do that feature extraction also by itself. And another point I can emphasize is there is an increased accuracy when more data is available. So compared to the machine learning, that's also another why people are talking about deep learning. Especially for the healthcare, it is trying to assist the doctors and clinicians for faster and more accurate decisions. So if you see the trend, there may be a lot of transfer learning, which is maybe beyond the healthcare. Maybe it is used for the general ImageNet or somewhere in the other fields. But still, this transfer learning is trying to help us, in, especially in case of these classification kind of a models. So another credit I want to give, it's even though we are talking about a lot of applications, it has a lot of background with IoT, the GPUs. A lot of people may understand what the GPU is. These graphical processor units, so where to do the lot of computations we require those. So a lot of digital data communications. These are also helping us to see the widespread adoption of the deep learning. Just before jumping to our healthcare topics, I just want to revisit the deep learning. When we say, even that is true for even general machine learning as well, we have different paradigm of learning. For example, the supervised, where we have the labeled data. So we talk about when there is an annotated data available, we can do a lot of classification, regression, using these convolution neural networks, some feed forward networks, or some kind of recurrent networks. I'll talk about some of the applications in detail. The second way of learning where we don't have the labels is unsupervised. So to give a number here, even though we are talking about three learning paradigms, if you see the supervised learning itself is taking almost 90% of the problems what we are talking about now. That's across the industries. I'm not talking about only healthcare. We are trying to solve the supervised way of problems, but that will be commoditized or maybe democratized in the next few years. Then more focus, I'm sure, will be on unsupervised and reinforcement, which is a lot of research is happening to different models also you are seeing, especially in the deep learning. So in unsupervised, we are talking about identifying the patterns. The autoencoders, the generative adversarial network is taking part in that. Even though it is relatively new, we are seeing a lot of attention. We are waiting for some killer applications even in the healthcare. Coming to the last paradigm, that is reinforcement learning. So where when we don't have the labels, or we need to have a sequence of operations, we need to have some kind of a reward mechanism, which is not same as having some kind of a ground truth or a label at the end. Those kind of learning patterns will be from the reinforcement learning. So limited applications at this stage, but I'm sure a lot of applications, maybe in combination with supervised or unsupervised, will come in future. With that background, let me set the context for what the trends going on in the healthcare. Some of you may agree to my points, what I'm presenting here. There are a lot of resource and access constraints when you talk about hospitals, the people, all those resource and access constraints. Then a lot of aging population. Maybe in India, we are talking about, we are pride of now, which ours is a young country. But globally, if you see a lot of aging population, and the average span of the people is going beyond 100. So we require a lot of technological support to support those kind of aging population as well. In one hand, there is a lot of shortage and of the clinicians, radiologists, pathologists we are talking. On the other hand, we are talking about increase in the number of procedures. And for example, Government of India is talking about Ayushman Bhava to cover the different insurance policies. So naturally, there will be more people who can have affordable healthcare. So there will be a lot of demand for these kind of procedures. Plus, diseases, whether it's a cancer or because of our lifestyle or whatever the food we are taking, we are seeing a lot of new diseases coming. So there is an increasing trend of these procedures and diseases, and there is a decreasing trend of the in turn shortage of these clinicians. So the only way to solve it is to complement the efforts of the doctors community with the technology. That's what we are talking about now in some sense. To give you some numbers, this is kind of a surprising number, but maybe for some of you, is the healthcare industry overall global worth is more than 8 trillion, which is more than any e-commerce or even the oil and industry, which we typically think is a big industry. But only 20% of the people around the world have access to the quality healthcare. So there is a lot of requirement to emphasize on the value-based healthcare. And what is the trend? Another trend is healthcare industry is going towards the data-driven approach. So to confirm any disease or treatment, we require a lot of tests, or there is data to finally prove that yes, this is kind of a thing and disease it is, and then this is kind of a treatment. So where definitely the deep learning can play a lot of role. And we see not just only the personal health, but even population as a whole, population healthcare data is also available. So I will talk about that. Another important point is 75% of the healthcare data is unstructured. That means maybe we are familiar with our reports, maybe when we go for a health checkups and all, which is neat and clean kind of a report, but still most of the data is unstructured in the form of images or text. So we need to do a lot of work there. And there is a trend of personalized treatment. The people who are affordable to do this healthcare, they want a personalized treatment or a better care. So all these trends in the industry is helping us to advance in what you say, the implementation of the technology to take the benefit of it. So that's comes to my topic on what are the top 10 applications. This is my view. So people may have a different view of the applications in ranking or rating them. But with my experience in this and giving a lot of, I have given a lot of references for you to refer as well. This is my list. So the first one I'll go with is medical imaging. So for example, a lot of classification or images. So what I talk about is in the next few slides, I'll talk about an application and relevant image also you can see so that you can relate to what I'm talking. For example, in medical imaging, we have, let's say, a lot of these modalities, CT, MRI, ultrasound, X-ray. So all those modalities also coming up with these kind of ideal models inbuilt, so which can do better classification, segmentation. Then how do you ensure the quality of the reconstruction of image? So those are the things across the modalities it is happening. When we process more images, the DL algorithms or DL models are enhancing its accuracy as well. So as we have more data, and it is, you can see the improvements there. So the pictures what you see here is kind of a brain images, so identifying the lesions or strokes. Then the second one could be on faster diagnosis. Is not just limited to the images, but typically the medical data, not just only images, the medical data is analyzing is not any trivial task. So the doctors are spending a lot of time and difficulty in analyzing as well because of a huge amount of volume. So how can the GPU accelerated DL can automate this analysis and augment the process of this decision making or the diagnosis? So now the trend is the DL help the doctors to analyze the diseases better so that they can give the better treatment. And second thing, as I can see the last bullet point that I'm saying, now we typically go for multiple doctors to take different opinion. And each doctor, as you see that in a critical situation, they may have different set of opinions. So I have a quote maybe in the end from Dr. Devi Shetty from Narayana Health. What his comment was, maybe in next 10 years, the doctors may be bound by the regulatory authority to take a second opinion from the system, because system is trying to analyze from multiple things. That may be a truth going forward. So we need to look forward for those kind of maybe the future changes, but what ultimately it should be helping the larger community. So if I go to the next one, so the third one, what I list here is early detection, because now we are using a lot of gadgets, whether it's your mobiles or this Fitbit or watches, you are getting a lot of continuous data. Why can't we use those kind of data and detect these diseases much earlier is another trend or paradigm. So it can help us to discover the symptoms as well. That's what I'm trying to show here in the third bullet point. And fourth one is improve the efficiency, especially for the radiology, because radiologists spend a lot of time. This involves a lot of complex analysis of the images or volumes. And how can I help or the DL models per se help the radiologists work in terms of pricing? It's more like prioritizing. So if it can identify or classify normal X-ray images versus the abnormal, maybe the abnormal he can give more attention in prioritization, so that he can spend good amount of time there, and the other ones he can validate. And as long as he has trust with the system, he can spend few seconds at least to make final decision. But otherwise his life is becoming easy. It's not just only the imaging part, but it can help the overall workflow improvement. There are a lot of effort of using not just only DL, even the broad spectrum of AI and optimization. And what is helping us at the end is improving the accuracy and the misdiagnosis means, as the report says, even though I'm not quoting exactly here, there are so many misdiagnoses across India or even in the globe wide as well, for a number of reasons. Maybe the doctor overlooked that point, or maybe he's tired or fatigued. So we don't want to take that chance, especially with the technology. So it can help the radiologist to improve the efficiency. That's what the fourth point we are talking about. The fifth point, if you shift the gears a little bit, is on how do I get a personalized treatment. Let's say the system has my medical history or past conditions, diet, stress levels. It may be coming from different sources, But maybe if I may not have the data, maybe with the data, whatever I have, maybe I can identify similar patients. That's also possible, because initially we may have a struggle to get each person's data. But as long as I have this kind of data, can't I give some kind of a health recommendations or personalized disease treatments and optimize those treatments is another paradigm people are working on, especially with the DL. So the same thing will continue or extend in little more complex way is how can we use the gene structure of a person? So which is a lot of research is going on here to build the precision medicine. So even though it's a lot of computational effort, but still the genetic factors like mutations will help to identify what are the things which are leading to these kind of diseases. Can we, what are the precautionary steps we can take it? So the key takeaway in these two will be or how the DL can help the building the personalized models. That comes to the next step, saying that drug discovery. So there are a lot of huge amount of data. If someone is familiar with this drug discovery process, you know it's a kind of a multi-year effect to come to the to identify the specific drugs and getting the approval. So a lot of knowledge and from multi-dimensional data which we get, we need to correlate, assimilate, and connect so that we can discover the patterns, which should ideally speed up the clinical trials research. But we should be very cautious when we are using the technology here, because unless we have the diverse data set, we may be biased with an unbalanced data. So there are even techniques to avoid this unbiased, but still we need to be very careful while building an applications using the technology to speed up the process. The next application what I can talk is on the robotic surgery. So even though the advancements in terms of actual robotics is helping, but the engine, the brain behind that is building these kind of DL models to help our surgeons to have more precision and fine detail while doing their surgeries. Maybe one example could be the cancer treatment. Even there are real world applications, as you might follow in some of the advanced hospitals, the multi-specialty hospital. They are already using these kind of robotic surgeries backed up by the AI. Even DL is also playing a role there. So the last slide in the top 10 applications will be on, we talked about personal health, we talked about medical imaging. Next comes is the population health. We are not trying to limit these kind of building the models of DL models only for a particular person, but we can build based on the population trend. We can use some kind of a regression and other techniques what we are familiar with along with this DL applications, so that our aim is, okay, how these kind of diseases, whether it is a dengue or malaria, how the spread is happening, how can we control that? So that is kind of population health. And the last topic which I pick from there is the information extraction. So as the iceberg is showing here, there's a lot of, maybe we are familiar with our standard DICOM kind of a format of EHR structure, but apart from that, there is a lot of unstructured clinical text and the notes, and then conversations now with the speech to text coming into picture, and scanned documents, manuals, a lot of knowledge is there. How do you extract that notes and to help us to anonymize by identifying the PHA information, or annotate, to do semantic analysis, inference? Can I do, okay, the moment the modality is giving me a picture, can I do an image captioning to generate a report? Or can we use this knowledge to build a chatbots? There are a lot of trends going on in that direction as well. So these are the top 10 from my side. And to just extend the discussion further, the DL plays role even in the neighboring domains of insurance and pharma is very well connected to the healthcare to improve the process of clinical trials, or the personalization of the premium, or prediction of the fraud claims, or treatment versus claims validation. There are a number of applications if we extend further the domains. So, but another acknowledgement I want to give to the other technologies, even though we are talking on the deep learning, there are a lot of speech to text where the doctors can converge, and a lot of the people are already using these kind of, with the advancement of Alexa or Siri, or a lot of even startups are also there in that. And then AR, VR, augmented reality is trying to help us to demystify what is actually happening inside. We can explain it easily to the people. Then Internet of Things, mobile apps, all these technologies are also helping the widespread adoption of the deep learning. Whatever I covered so far in last 20 minutes on the top 10 applications, in the next 3 slides, I want to, I'm not talking new things there, but still I want to see multi-dimensional view. In one dimension, the first one, what I'm showing it to you here is, People may think healthcare means is only hospitals, but what I'm trying to present, this is our own company, Philips' view of a health continuum, where it is starting from healthy living, prevention, diagnosis and treatment. This may be happening in hospital and home care. There is a hospital to home. There are a lot of other things in the healthcare continuum which is beyond the hospitals. So the deep learning applications are coming at all the stages. To give an example applications, let's say healthy living in prevention. As we talked, we are getting a lot of different health parameters from our own devices, maybe from different companies, doesn't matter. So as long as you have a lot of information in your personal health or your lifestyle parameters, we can identify and build the models to identify the normal or abnormal, and we can take a right action at right time. So sometimes why it is important is, we all know prevention is better than cure, and there are a lot of effort going, and the cost of saving a life is definitely better if you can identify, let's say, heart attacks. If you can identify a couple of minutes before or even a couple of hours before, nothing more than that, right? So we can save a life. There are some diseases where people claim, maybe with limited accuracy, they can identify that kind of diseases maybe a couple of weeks before, so, or even a couple of months before, depending on the type of the disease. So those kind of that is coming with the help of a lot of data availability and model building. Then the diagnosis, we can do the treatment as well. So we can try to personalize based on these multiple DL models and identify and we can make the life of even a radiologist or a doctor by identifying the relevant slice in the entire CT volume, what is more relevant to him. So using the technology and DL models. At the same time, home care, we have seen a lot of aged population as a problem, and then we can alert when somebody is in an emergency. The physical devices may be coming from IoT, but the entire logic building, there is a credit goes to even deep learning. So the next dimension, what I'm trying to look is, okay, I know there are different types of deep learning, something like a supervised, unsupervised, and different reinforcement. Can I get an example for each? So I'm trying to address that point here. In the supervised, you see there are feed-forward networks, convolution networks, and even recurrent networks have the long short-term memory and GRUs. So I'll talk about the other ones as well. So if you see the supervised learning, so it is used in personalized treatment. So specific example can be type 2 diabetes or cancer treatment. And in case of population health, one example could be, how do you predict the malaria or maybe dengue on those kind of outbreaks? Then in case of standard image classification, that images can be coming from different modalities, but it can be cancer, lung cancer, chest TB, classification examples, or we are using even for the segmentation as well. Then for the radiologies, how do you detect the healthy versus the cancerous tissues, so that the person, we can do maybe the right treatment for the person. This is one angle. The second one is using the recurrent network. Typically the recurrent networks, as you maybe agree with me, whenever there is a sequence modeling, typically we require these kind of recurrent networks. That goes same with our healthcare as well. To have the early warning, because I have a sequence of data, how particular parameter is changing, I can build a model and then alert at the right time. Similarly, the precision medicine. So how do you, I will explain a little bit further these kind of, because we have done some work in this as well in a detailed slide. But at this stage, the precision medicine is also backed up by these recurrent networks to identify specific, okay, as an example, how do you identify a dosage of a BP level or a sugar level? When it comes to the unsupervised learning, all these GANs, generative adversarial networks, or the autoencoders, it is helping in the drug discovery, specific drug validation we can do. Or there are a lot of types of these GANs. Maybe I have even one slide or two slides on this. I will explain that time. On specifically for the data augmentation, because we are talking about a real world situation where I may have millions of images for normal cases, but I may have hundreds of cases only for abnormal. I can't build directly model without solving that class imbalance. How even deep learning also can help even the data augmentation along with our standard statistical methods. I'll talk about that little more detail. The last one in that dimension is the reinforcement learning. There's a lot of attention of the deep reinforcement learning also coming in picture, where something like a deep Q network can be an example there. The right treatment identification, where there is a sequence of treatments I need to take, and then how the people are responding, and I need to make a decision. It's not just going by the label. It's not a universal treatment for all. So in those cases, the reinforcement learning has a good application. So if we switch gears a little bit on the another dimension, So maybe we are talking about, I know a lot of, I may not be master with this healthcare kind of a domain, but I know I'm good at handling the text data, or I may be good at handling image data. So how do you give an example of different types of data in the healthcare and specific applications? So that's the way I was looking in this. So if you take the blood reports or the medical test reports, maybe most of them may be numerical and categorical. So if maybe you need to do some kind of a pre-processing, if you, I hope you will agree with me, because you have some basics of the deep learning. I can't directly take the text or image and dump it to my network, right? So we need to do some pre-processing. That's why I'm highlighting that point as well. But application could be some kind of a classification model. In case of medical reports, let's talk about the text data. We can use some kind of a TF idea for much more advanced word-to-vec. This word-to-vec is also based on unsupervised deep learning for that matter. We can do a lot of summarizing of the medical report or automatic report generation. If you talk about the X-ray, then we can talk about, these are kind of a two-dimensional images. We may need to do some kind of image normalization. We can use for classification, segmentation. I'm not talking about specific anatomy here, because you can do whether it's for lung or maybe the heart or cancerous, different departments. So it all comes from, I'm not giving the dimension of, okay, I may not be the right guy to give the dimensional view of a personal body and how you apply that. That also could be the another fourth dimension to look at, but I'm giving more from a technological view here. So if you continue the discussion, we have, let's say, a lot of modalities here. Let's say CT, MRI, and ultrasound, where the output can be the 2D or 3D kind of a videos, where I may need to do some kind of a processing at a slice by slice level. There are some kind of a convolution 3D kind of thing as well coming, but still a lot of processing is happening at a 2D, but depends on your choice. How do you process? But the applications could be an object detection or a lesion detection or a classification or a segmentation across different modalities. Then the new thing which is coming is doctors and technicians may not have all the reports to typically when we attend conferences, what the common complaint from the doctors is they are not happy with the typing everything, whatever, because their natural way is to converge. So anyway, the speech data also we can convert to text with much more accuracy these days. Once we have those kind of speech to text conversion, we can use all the medical reports, what we talked about previously, the text data. So maybe extra step is speech to text conversion, but we can have the repository or the knowledge building on top of that. The last type of data is maybe a general signals, something like a ECG, EMG signals from healthcare, where you may need to convert those signals also some kind of vectors, because ultimately whatever you are building a classification or segmentation and all, our models require some kind of a vector form, as you can agree. That's where we require some kind of a pre-processing, so that we don't have to emphasize. We may have some kind of a specific images. Let's say you are using CNN, or maybe sequence data you are using LSTM, but you don't get individual different algorithms based on the type of data. Once they are converted into with the pre-processing to the vectors, it doesn't matter really for the actual models what you have seen feed-forward network or a recurrent network to really apply and make sense of the data. So what we covered in the last close to half an hour is the high-level applications in a broad perspective. But I want to utilize the time to go a little deep, and each topic we can talk about an hour, but in the interest of time, I may be spending 3-4 minutes each for 4-5 applications, so that you will get some sense of what we are discussing. So to start with, we already talked about the personalized medicine as an important application. So here, the personalized dosage of medicine, I may be giving my own application where we patented this year, but I can make it a general view here. The traditional approach, what we see here, okay, let's talk about a chronic disease person in our home, maybe our elderly people. They may be taking some doses of a BP or a tablet or for a diabetes. They may be having a regular pattern. Maybe once in 2-3 months, they may go to the hospital to check up. That's what the traditional approach we are talking about. So this stepwise, they may increase the doses or decrease the dosage. But what we are talking on the DL solution is one dimensional is, even though we are talking about 2 steps, it can be multi-step as well. We have a lot of information, let's say what he's eating, or what is his lifestyle parameters, whether he is really exercising or whether he's really traveling, or his clinical parameters, is he taking the doses regularly, the prescribed doses. When we capture those data, I can build a multi-step kind of, and that we, as you appreciate, this is kind of a sequence modeling, right? So typically we need to use some kind of an LSTM. long short-term memory kind of a network. And that too, what we tried was something like an ensemble LSTM techniques, which help us, okay, take all these lifestyle parameters and clinical parameters to identify what could be the BP level as a step one. So the second step could be, once you have, it may be a BP, or it may be combination of BP plus sugar plus something else. So when you have these combination parameters, maybe individual models are helping us to predict what could be the individual level of the BP and all. So that the next step could be, as a combination of all these parameters, what could be the dosage level for a particular medicine he need to take. So we can help this personalized treatment by building the DL models. This is one example I was talking previously. So if you further go to the next application, let's say medical imaging. So some people may believe, okay, the research, the reason to give this picture, the credit goes to NVIDIA. What they are trying to showcase here is what kind of percentage of people, especially percentage of papers, especially in the medical imaging, the trend is going towards with a focus on deep learning. If you see in the recent years, it's almost like 22 to 125% of the papers across the top conferences of the medical imaging are having some amount of deep learning in place. That shows how everybody wants to try. Maybe those are solved problems in machine learning or traditional image processing, but still people and the researchers want to check how it works with the deep learning. Some places there may be a tremendous improvement. Some places it may be delta improvement. So that differs, but still the trend is to use this kind of CNNs, whether it's a 2D or 3D, especially in the imaging. And the another important reason for that is also because we need not from scratch develop the models. So we can use the transfer learning, maybe from AlexNet, GoogleNet, all those based on specific applications. And our development time is also a little easy. But to build a sophisticated model, it's not a trivial job. I need to admit that. But still, trying in the initial one for the paper purpose or for the research, definitely people have no limitations on that. Another one, because we are talking from the industry perspective, not just only the research in the medical imaging, what we are talking about, these kind of DL models should port to a CT or MRI or ultrasound or any of the modalities, so that we can get, okay, that should improve the quality of the reconstruction of the image. Maybe should do a faster reconstruction, or can I reduce the dosage of the radiation, let's say in X-ray or CT, but still not compromising on the quality. So these are the cases where people are experimenting and having some good success as well. I hope that will continue further. But for the people, there is an interesting, I have given a reference down here. This image is coming from there. The other nicely put together where the deep learning is used in medical imaging. You can see it is starting from mammography, the breast cancer, and then brain, then some kind of a chest, even diabetic retinopathy, different classification examples or segmentation examples, multiple examples, but you will get a fair idea if you're really interested in the medical imaging, how maybe the literature, the research is going towards. If I continue the discussion further, the third topic in detail, what I was talking here is explainable deep learning. So here what I'm trying to emphasize is, okay, the deep learning is working, but maybe as of now people are talking about more as a black box. Okay, I have some data, I thrown to the network, maybe from the transfer learning, I haven't built the network from the scratch, I'm getting some results. But here the results means what? Maybe I can talk about accuracy, sensitivity, specificity, all the standard measures, right? But still, only with those, it will be difficult in this domain to convince, let's say, the doctors at the end, because they need to establish the trust in the system. So it's not like a hard coded. So how do I believe that, okay, there is always a training set, test set, I can give a lot of data in terms of these many millions of data points I try to build the model, but still that is only one angle. That is definitely important. I'm not saying that is not important. But on top of that, in the mindset of clinicians to establish the trust, there should be some other methodologies to demystify what is happening in the deep learning. This is the effort towards that, where can the localization and feature visualization techniques, we have some algorithms, even we implemented in Philips, it's part of our Philips Health Suite Insights, but more or less these algorithms are available even in the literature as well. What we are trying to help is, we know from literature or theory, each neuron or filter in a convolution neural network is responsible for detecting a feature. Maybe initial layers, maybe identifying the edges, colors, or shapes, but later part of the higher layers, maybe complex features as localization, textures, and all. Those are we from theory we know it, but how do you prove it? So that's what the next research is going towards. And features detected by last layer should be more discriminative, otherwise you can't make a decision. So this is the same what we are talking in the words. I am trying to use the algorithms which is available in literature for anybody to try get some kind of pictures like this. What I mean by that is this is actually twofold. When we say feature visualization or explainable deep learning, that is to help even the end customers, let's say in our case clinicians, that is for mainly the last let's say the three pictures. What we are talking about there here is we have some algorithms like a discriminative localization. I'm not going in detail, but there is a good references if somebody is interested. Some kind of a class activation map or a gradient based class activation map, silency map. What are all this trying to tell? There may be different algorithms like this, but what it is trying to tell is, let's say we built a simple model of chest X-ray abnormality. Which the simple model is okay. We trained on million images. It is talking about whether the chest X-ray is normal or abnormal. It's very good in terms of accuracy, specificity, sensitivity. But still, along with that result, if I give the doctor or end user, let's say, a highlight of portion. Let's say this chest X-ray is abnormal. This is abnormal because of this portion, some kind of a heat map or overlaying on top of input image, so that as an engineer, even if I see, I might have built the model, but if I see this particular image, I can't say whether what kind of abnormality is here. But from the lens of a doctor, immediately the moment he see it as an expert, he can say where the what is wrong with that. So we are trying to try to take the shoes of the doctors or clinicians and see from the technology can we address that problem. So it's not just only the numbers at the end, 90%, 90% accuracy or 99% accuracy. That is all definitely good because we need to show the validation mathematically. But at the end, if I give a new image and pass through this our algorithm or API, it gives this kind of image that will give us hopefully more trust to adapt these kind of technologies. That is for the clinicians. But other two parts, as you see here, this is more for the data scientists. Even for our as a data scientist, our day in and day out job will be maybe tuning a lot of parameters, hyperparameters. So how do you reduce the number of filters or increase the number of filters? This is not like trivial question, right? Maybe I can take some transfer learning, start with 3x3 filter or 5x5 filter. But what is the ideal for my particular data or problem I'm solving? So that also help us in terms of, say, I'm trying to give a snapshot of one layer which of the same chest X-ray of a activation map and deconvolution. What does it mean is activation map is more like in a forward pass you do you convolve features and then pass through an activation function. The result is an activation map where ideally you are trying to map the pixels to the features, whereas in the deconvolution you are trying to map features to the pixels. Is trying to reconstruct. Maybe if you tap the layer, I have 10 layers, maybe I might have tap at let's say fifth layer. So far how the learning is happening, can I reconstruct that back by following the reverse operations? That's what the deconvolution is trying to do. Both the confirmation map and deconvolution, what they're trying to do here is identifying, okay, at each filter level how the learning is. Suppose for all of the images most of the filters are not firing, that means I may not require all the 64 filters. So that can be one kind of a guided approach. So we can take advantage using this explainable learning both to the data scientists and clinicians, and even this is going to play a role even to get the approvals for some kind of FDA approvals or any regulatory approvals. So that the reason is we are trying to explain why the network is trying to work. That's the reason we are saying it has a good scope. And the next, if I switch the gears there is, okay, I might have spent a lot of time, or maybe there's an engineers or the researchers, we build a lot of models, but the target deployment environment may not have all the GPUs and all, may not be required to have, right? Because that model may need to run, if it is running in a cloud, it's a different story. But if let's say if I want to run it in a mobile or maybe in my desktop computer in the hospital, in the real time. So how do you get the good performance there? That's what the speed to diagnosis I'm talking about. So people can use, let's say if you have a GPU for better performance, you can use NVIDIA TensorRT, or Intel chip is very common to have in most of our desktops, right? So how do you use the Intel inference engine to speed up? What I mean by speed up, let me give an example here. So before telling you how it works, I want to emphasize the point. Suppose if I build the same chest X-ray or some kind of a bone-age regression model, I built all the model, but in real time, when I give an image, it should process and tell me whether it is okay. It's kind of abnormal or normal. Or in this particular example, what is the age of what is that particular bone age using the regression model. So I can do hardly 4 5 images if I have a small desktop per second. That's what the FPS frame per second means. But if you use some kind of inference engine, I'm not changing the model, but I'm trying to optimize how it works. Definitely you can understand it's not only software optimization, a lot of hardware optimization. That's why you can see dependency of Intel or Nvidia coming in picture, because they can have a lot of math kernel libraries underlying to do the faster execution, which can result into up to, let's say, 40x improvement, what I'm quoting here. But even we have much more based on the model. We have even beyond that the performance. So how they are doing in a nutshell, if I emphasize that point, the input can be your trained Keras or Caffe or TensorFlow kind of a model, but output is converted to some kind of a general form, kind of an XML and bin to convey the network architecture and weights. Finally, it uses internally those batch normalization or effective computations, so as to optimize that model and give the best performance. This is also gaining the momentum, because this is towards, okay, I should be able to run even with a USB stick, maybe with our own desktop, or maybe in the boxes what I talk about, that ultrasound or CT or MRI. So then only widespread adoption will happen. So the last one in detailed discussion for us is synthetic image generation. So I already talked about a problem of unbalanced data. That's not a new problem. Everybody who builds a machine learning or deep learning models, you appreciate there is a problem of class imbalance. Maybe you might familiar with our statistic models of a SMOT, synthetically do that oversampling and do it. There's like standard techniques like that. But how can I use the deep learning approach, especially I talked about maybe supervised till now, but I want to give a flavor of unsupervised as well, where we don't have annotations or the labels. What is happening here is the aim is to generate for our data augmentation new images. How we are doing it, if you see on the right hand side, I have implementation of two networks, especially the generator and discriminator. Both should work in tandem as a zero sum to achieve a Nash equilibrium. So how it works is, initially I'm giving a random noise to a generator and trying to generate some sample. And the role of discriminator is, if the because it is taking real world images and the fake images join, the role of discriminator will be to identify real and fake. Maybe initially, as you agree, if I give some noise and build some generator, I won't expect a magic of getting a image. And that too, I'm talking about class specific images. The reason is I'm trying to generate the images for the minority class, where I don't have enough data. So in that case, but when as the training phase goes with the back propagation, both the discriminator and generator tries to improve. Going forward, maybe generator reaching to a level to generate the fake images as close as possible to the real world, so that it will be difficult for the discriminator. Otherwise, discriminator is always winning, right? So the Nash equilibrium says the generator should and discriminator should not win over the other. So the ideal situation could be generator is producing as close images as possible, so that I can use those images for my data augmentation. The whole purpose is to build a better classifier. So that's the idea of the GANs. And we used, and what I'm presenting is the initial results from using, let's say, our cervical cancer data. But to do that, the general GANs also not helped us to build directly to reach to a level of these kind of 64 cross 64 or 128 cross 124 images. We have done a lot of tweakings or hacks to what kind of you can see in literature 20-30 different GANs. Maybe people talk about DC GANs, that means deep convolutional GANs or conditional GANs, auxiliary class. I don't want to bombard with those names, but there are multiple GANs for our purpose. What we tried with conditional and auxiliary class GAN, what is so special about these kind of GANs is the same extension of the previous one. It also has the generator and classifier, but extra thing is not just only noise goes there, but the class, okay, whether it's a normal or abnormal, so that the generator generates the fake image, and the discriminator also, in case of this AC GAN, produce the images at the same time produce what kind of class it belongs to. So overall, we are trying to learn not just only the probability distribution of the images, but even the distribution of the classes. So that resulted into these kind of images. I'm sharing only an initial result, but even as the number of epochs increased, we have some more better images. But at this stage, it's more of art than science using these kind of GANs. But I'm sure this also will come to the mainstream very soon. So far, we talked about the top 10 applications to view that in multiple dimensions, and then maybe 4 or 5 applications, specifically 5 applications I talked in a little more detail. So the last 5 minutes I want to use to bring to you what are the different challenges. Maybe people can question, we have a lot of potential, but compared to, let's say, other domains, the usage of DL may be little limited, as you see in the real life. There are a number of reasons. One reason could be the DL is in early stage, especially when it comes to the let's say the healthcare. And this is not because the technology is not matured, but there are other reasons for the wide adoption. For example, acceptance of the physicians. And we can't, our aim is not to replace the doctors. There is no question of that, but we need to, but there is a fear of replacement, as we could see that, but we are trying to complement. So, and slowly the people are trying to adjust to that so that the challenge can be overtaken. But we need to establish the trust. It's our responsibility, being an engineers or data scientist, to our doctor community, that we need to emphasize, yes, the technology is working in these situations. It may not be 100% always. At least that model should be able to tell these are the cases which I can tell, give a accurate prediction or accurate classification or segmentation. In the extreme cases, anyway, you take the choice. But we need to do a lot of clinical validation to do that, and repeatability of results. It may work for one kind of a problem, one kind of a people, but what will happen to other set of community, or where their demographics change, or maybe their lifestyle changes? I may not be able to generalize it, but how do you see the repeatability of results, or how do I customize my DL models built for one set of people to the other set? Maybe in India we have a lot of diversification, right? So the next thing is, even though there is a lot of potential, we say that a lot of data is available, but the quality and diversity of data building models is crucial. One is technical side of having the access to the data, but another thing is there is a lot of privacy rules, and a country or hospital have their own rules to access this data, and we are bound by the regulatory approvals. Because something wrong happens, a decision making, it costs a life, which may not be the case in case of our e-commerce or retail or those cases. Even if the wrong recommendation comes, or this one, it's okay, they can easily correct it. But it is much more emphasized in healthcare. You can see those challenges. When it comes to the platforms, there are so many open source platforms, and even Philips has a health suite inside. A lot of information is available in the internet. I given the link as well. Apart from Philips, even we have IBM Watson, Google's DeepMind, Predix. There are a lot of, and I just listed only some of them here. And you might be knowing there are a lot of startups even to take care of what kind of platforms can help to build the models quickly. So the future scope I am expecting is the approvals to use DL models to come to the mainstream will be on the way. The FDA, maybe for the US, but even for our department, Government of India also has their approval system. That may go to the autonomous robotic surgery. We can see a lot of advancement even in that, personalized care as well. As we see, prevention is better than cure, and in IT it is a common term to see the shift left strategy, right? So instead of fixing a bug later part, so why can't I fix it in the beginning? So the same shift left strategy we can apply here. So I will give you an interesting point here. So typically, let's say how the hospitals will be more profitable. Maybe more sick people, if they join, the revenue will be more. But that is it ethical? That's a different story. But as long as they need, the hospitals are bound to serve the people who are in need. But ideally, as a societal perspective, we need to think from the perspective of the number of people who are falling sick should come down. How do you do that? Say there is one example here. So the people are talking about getting the health insurance premiums, but after that they are not caring for how we drink, or how we, let's say, use our lifestyle, what kind of food we are taking and all, right? But there is some new paradigms coming where they will collect the premium for us, and at the same time they will monitor our activities, and they will help us to protect the person not falling sick. Then they're making money, right? So because they're helping us, in turn they're taking the premium for us, and at the same time they're helping us not falling sick. so that that's becoming a new revenue generation model. So people can think of these kind of new things. Ultimately, we should have a better, healthy society. Then wide acceptance by the technology to the doctors. I heard some efforts will be there to include AI or this kind of MLDL as a subject in MBBS. That can be a good start to bridge the gap so that we can work together, and technology should be complementing the doctors. As I already mentioned this quote from Dr. Devi Shetty, so there will be a lot of second opinion taking from the software, by the software for diagnosis, which may not be 10 years. It may come a little earlier or later, depends on how the development goes in the technology. But I'm hoping for that, so that it will help us to finally to build a better society. So these are my concluding remarks from summary wise. So we are exactly on time. So what we have seen is we have seen the huge potential. What are the trends from the healthcare? How the DL can solve different types of learning, supervised, unsupervised, and reinforcement. I try to give some 10 top applications what I feel in that is not specific to any company or this one that's a generic. And I try to give some coverage of detailed coverage of some of the applications where Philips worked and where I worked also personally, to give you some kind of a perspective on what challenges we face and where we are heading to. Then, but still there are still a lot of challenges to overcome, but maybe some kind of explainable DL or building the robust model, a lot of clinical validation can solve those purposes. And we need to pass through those approvals to go to the widespread adoption. And that's what the democratization I mean. And the outside developments of DL, such as speech to text, IoTI, they are also definitely bound to disrupt the healthcare. So that's kind of things what we covered so far. And along with you, I'm also looking forward to live in a better society with affordable healthcare through technology, especially the DL also playing a good role in that. Let me take a pause here in the interest of the times, and we can open the forum for the questions if you have any.
Thank you, Sunil, for this wonderful presentation. It was great indeed. So now let's just begin the Q&A session. So the first question is, there are two questions from the same person related to each other. So I'll just relate both the questions. So the first one is, what is the scope and scenario involved in genetics, and how efficient DL would be in genetic research?
Okay, that's the first question, right?
Absolutely.
Yes. So definitely there is a lot of scope for DL models to build in the genetics, but only at this stage, even though there is a lot of scope, it requires a lot of, as I mentioned in one of the comment in the same bullet point, is it requires a lot of effort to analyze the gene sequence. We require powerful computers, and time may be taking a couple of days to identify that mutations, and especially the inner details at how they are related to a particular, how they are constructed, and how can we have different gene structures mapped to, okay, these are the let's say adding to these kind of diseases. So there's a lot of effort going on, especially there are government projects as well. And there are even I know a couple of projects which are even across the world, so where government of India is also taking part. But only thing is, maybe it will be difficult for a startup or a small environment to take up that research. You should have a part of the community so that you will get access to the data and you have a large compute power. Especially when you demystify all the gene sequences, naturally the next step is to use the DL to build the models. Finally, if you have a good amount of gene sequences, the DL can play a good role in building the model. Finally, that can help us building, okay, these kind of diseases can not be there. Maybe people can argue whether it's a good or bad, but it may be handcrafted kind of a babies may come in future if you have progressed in that, but it's a little time to go there.
All right. Thank you, Sunil. The other question is, what would be the percentage of efficacy of diagnosis expected with DL when it comes to diagnostics?
Okay. So I appreciate the question, because it is nowhere no person can claim 100% accuracy per se. But actually, there won't be any direct answer in terms of whether it's an 80%, 90%, because actually depends on the model. If you ask me a specific model, which where we are involved in building a model, let's say I talked example of a chest X-ray type of it, right, where we are able to reach almost like a 99% of an accuracy. But because we have access to 99, not specific to 99, let's say 99% of accuracy, because we have access to millions of images, we are able to not only accuracy, even the specificity sensitivity is also quite good. So at the rate of 90-95% type. So what I mean to say that is the data is more like garbage in, garbage out. So you need to have good quality data. That's still a challenge because we need to see we need to do a lot of data processing. That's what why another it may be looking like data science is only the fascinating thing compared to the data cleaning and or data wrangling. But the reality is you need to spend, maybe if I give a number game, maybe 20-30% effort is goes only to build the model or fine tune the model, but rest of the 60-70% goes into the collection of the data, cleaning of the data. That's the actual real hard work goes there. So when you have good amount of data and that to diversified data, definitely it is possible to go to a level of, let's say, 99% kind of an accuracy. So if you have good amount of data, to answer your point, we can reach to that. But if you have only small sample and going expecting that 99%, it may be a little difficult.
All right. The other question is how deep learning techniques can be used to detect cancer/tumors in early stages itself, bracket stage 1 of patients, and help the doctors identifying and preventing cancer tumor growth.
Good question. So, and we see even in India, a lot of cancer and lot of different cancers, right? It may be initially we heard only, let's say, breast cancer or mammography is the more common disease in the in our ladies. But if you see now, they are talking about different lung cancer, mammography, or different type. Whatever the part you talk about, there is some kind of a cancer being associated, which is not revealed to identify. But what we have seen, especially to identify the stage 1, is as the people going towards the regular checkups, at least the community who is educated or this one, they, as we are crossing, let's say 30, 35 or 40. So there is a habit which is trending to go for health checkups, and that too we need to watch. That is one kind of a data point for us. And second data point is people are using a lot of their, okay, if there is any change in your lifestyle, sudden weight loss or this or any changes, but you may not be physically identifying, some maybe your computer or maybe your mobile or even your Fitbit watches, they can also identify the change in different parameters. As a human, we may not be able to correlate all that, but if you pass these two systems, and there are a couple of apps coming up, still not matured at this stage to be frank, but still once you combine the data from these health checkups and the regular data, it is possible to at least some I won't say 100% all that, but at least early detection is possible at some stage based on the type of cancer. But a lot of models are building the models to analyze different symptoms on what kind of cancer we are talking about is still undergoing. But to leave the thought there, it's an active research. I know some couple of startups are also working on that, along with good hospitals and specialized cancer hospitals, to relate the data what we have from the patients, so that to identify the early stage. And if I want to extend the question as well, one is identification, and then second is even a lot of effort to treat that even at a stage 2 or 3 also. That we know a lot of people in our own families who was survived for a couple of years and later on, right? So that also coming, DL is playing a lot of role in personalizing the treatment. Does it that answer to the point? Yeah.
Yeah. The next question is, how many of these applications do you see being used in mobiles?
Good question. So the applications, especially if you just type even in the Google Play Store or even in your iPhone, let's say some identifying something normal or abnormal, maybe it not for, let's say, chest X-ray or maybe some kind of a CT volume, because you can't give that in a mobile, right? But as long as you can give, okay, I have these symptoms, maybe something changing for me. If you give these symptoms, they can also, there are applications where even I tried myself as from third-party apps, which help us to tell what's wrong. Maybe do we need to consult a doctor, or is it something to worry? So those kind of symptoms, if you give capturing, already they use a lot of DL models at the back end to help us to see, okay, this may be diagnosis. I'm not saying everything it is correct, but at least we can take a second opinion type of it. Just like we ask our friends or this one, okay, I'm having this, okay, what could be the reason? So that can, as a friendly suggestion, it can give. That is one I have seen in the mobile app. And second thing is, if you have a lot of data, all data may not be stored in a mobile, but as long as you have access to maybe your repository, your drive or something, there are models which can run even some kind of a medical image classification, small models, or even some kind of a text data. These kind of models are also coming towards, especially because TensorFlow kind of thing, it has a TensorFlow Lite. So that means there is a framework, even it can run in the mobile. So those kind of applications. And then maybe beyond DL, maybe they can identify something like, beyond healthcare, they can identify something like a face recognition. There are a lot of apps, I think you are appreciative on that. But even in the healthcare also, to simplify the point, you can, the symptoms diagnosation or some kind of a classification, it can still do.
All right. The next question, or maybe you can say the second last question, will be as you mentioned, 90% of the problems today are solved using supervised learning. What examples
Yes.
in healthcare need unsupervised learning?
Yeah, interesting. So when I say that statement 90% is not just confined to the healthcare, I'm actually re-quoting, if you know the Andrew NG, he's a famous person in the community, right? He quotes, and even I second the thought on that. So even in the healthcare, what I mean by that is, as long as we have labels for the data, we are, whether it is a classification problem or a regression problem or segmentation, we are able to solve that. But especially the unsupervised learning, why it is coming picture is, we have a lot more data than what is there for the with the label, without annotations available lying in the hospitals. Okay, without annotations, I mean. And now to do the annotations with the doctors, it is a costly affair. So the straightforward applications of the unsupervised learning is to extract the features from any of this. When that you can talk about chest X-ray, ultrasound, or MRI, any of those images. So take that, wherever there is no annotations, can you add the annotations? Can you extract the pictures from there? And I talked about the GANs application. The GANs is purely an unsupervised learning. How do you augment the data? How do you extract the features? So once you build that annotations and maybe validation with a doctor or a corresponding person, maybe that may go into the bandwagon of the supervised, because now they have some let's say the labels or ground truth or annotations available, and is already proven in supervised. But what is the gap is, how do you establish, or how do you minimize the effort of the humans or doctors to do the annotations? Can the mature technology can help, especially the DL, which is still ongoing. I'm hoping it will take center stage in the coming years.
All right. The last question for this session is how to get data. This regulation allows hospitals to share personal diagnostic reports for DL.
Okay, that's interesting. The reason is, no. If I ask you back the question, who wants the data? So, but I can't get the responses. But let me tell. You may think the hospitals are owning the data, but no. That depends on country to country. Even in India, the person owns the data. Only thing is, these hospitals, while we register, typically they take our consent. Can we use this for our research purpose? Or explicitly also they can tell you, okay, this data we are going to use it. As long as they have explicit permission, then only the hospitals or doctors can use. Otherwise, the owner of the data will be typically the person. So, but there are some open source data points which, and after anonymization and after cleaning up the data, there are some sources, especially the Kaggle or even the lot of US universities are giving us. So that can be a good starting point for the startups or the other people. And second point could be, you can partner with the hospitals and then take those consents and take the realistic data, so that we can build the good models for our Indian populations. Because I can't directly use the Western world models which we build. We need to fine tune that further.
All right, we have another session at 3:40, so I guess we need to wrap up now. So thank you so much, Sunil, for this wonderful presentation, how technology is smartly assisting doctors to diagnose the diseases at a prior stage, robotic surgery, how AI is transforming the healthcare sector. It was absolutely an enriching session. And to all of you, I just want to convey one more thing, that the next webinar coming up from our side, that is the Product Council, is on 29th of November, under our product management webinar series, which is the topic is demand slash lead generation by Paroma Sen. So see you on 29th, and thank you, Sunil, again for your time and
Thank you.
effort and your presentation. Thank you, all of you. Have a nice day. Take care. Bye.
Thank you. Bye.
Thank you. Thank you. Bye.